If I do falter, please let me know. We're going to have a little change of tact here. We've heard a little bit about Gcmaf, some of the things about the immunology of people, and this is the testing time. My name is Rod Smith. I represent Macro Innovations. My colleague Emma Ward is with us today, and out of the two of us, we drew lots, and I was the lucky one to win to talk about what we actually do. So this is a presentation of some of the data and the testing that we do on the batches of Gcmaf that we get from immunobiology. There you are. Macro Innovations, Emma and I have worked in the vaccine development, drug development field for a number of years. Myself, it's been over 24 years now. I kind of have expertise, if you like, in tissue culture, monoclonal antibodies, expression, assay development. I've worked at the European Collection of Animal Cell Cultures for a number of years, and hybridomes shows, and any type of cell line that you've got, I tend to be able to grow. I've done a lot of work with HIV and herpes simplex virus vaccine development. Emma's got expertise in downstream processing and analytical techniques. So Immunobiotech approached us with an opportunity for us in business sense of setting up some testing on this compound, this molecule Gcmaf, and for us to develop ways in which we can identify, show that it's safe, show that it's efficacious. Gcmaf, what is it? It comes under a guise of names: GC protein-derived macrophage activation factor, which is what we call it, Gcmaf. It's a group-specific protein. It's got a vitamin D binding protein, so it comes under a number of terms in the literature. And when you look through the literature, all of these terms are all relevant, but for us, we call it Gcmaf. It's easy, we understand it, we know what that means compared to the other molecules. Some of you are already aware and know what it is, but what is it? Here it is represented in amino acid sequence, and we can see it's already been expressed this morning, the vitamin D binding region, the actin binding region, and then the bit that we're all interested in is this little section down here which has the sugars on, which was so very well displayed by Cornelius in terms of the scissors and the cutting of the sugars. So this huge molecule is what it's all about, but this little section here is what gives it the efficacy and what we're interested in testing. So it's kind of a big job to do for such a small little change. I too have my own little section here, which is taken from some papers. This is the threonine at 420 that was mentioned. This is the N-acetyl galactosamine here, and it has the two sugars, the galactosamine and the sialic acid on the end. Those two are cleaved just here and here, and it produces Gcmaf, which is the activation factor, which we're trying to identify and monitor as we go through from batch to batch. So why do we test? We're testing for these primary reasons: the safety of the product. As you can all understand, what we're interested in is something that's safe. No one wants to take anything which is unsafe or been seen not to. But it's active. So you all want to take something that's active, that's not just a buffer or water, or not very diluted, that it's almost inactive. And then we're looking at consistency from batch to batch. So those are the three primary things that we do. So it puts us in a good position to have a look at all the things that we can do. On the website, there are a number of tests, 9 in all, that we do currently at the moment, and we're also researching into how we can improve those and what we can add to the portfolio that we do. Sterility. We don't do sterility in-house, we send that externally, so the samples that come to us, we send them outside to an external testing house. They're all set up for that kind of activity for GLP, GMP compliance. We paid for our own validated assay which suits our needs, which meets both the USP and the European Pharmacopoeia standards. So we have a validated assays that we've gone through with large numbers of samples so that we have consistency when we send the next batch off. Endotoxin, that's quite important. Endotoxin, as you know, can cause anaphylactic shock. So we check for that and make sure that there's nothing untoward in the batches that come. We use a Lau method, using a Charles River piece of kit, which is accepted by the FDA with its results. We do this in-house, so all our results we monitor and keep going. So we keep a battery of them to know where our endotoxin levels are. And of course, if they fail, things are rejected. We do a protein quantification using a BCA assay, and we also test the pH. Those are kind of the physical biochemical assays that we do, which in themselves give you a good indication of what the product is like. But for us, when we know and we start to find a standard, we're looking for that consistency all the way through the process. We do some identification, which at the minute, we do the simple things, if you like, the SDS page, which people are very familiar with. We use non-reduced samples and we use silver stains to compare profiles of batch to batch so that we know we are consistent in the product that's been supplied. We do some Western blots. And as many of you will know, Western blots, there is nothing that we can pick up that isn't globulin, but we're looking for something which is specific for Gcmaf. So we've screened a panel of lectin, and we've got one or two which are really quite good, and I'll give you an example of that. We do reduced and non-reduced. We use the Helix Palmatia and a couple of others which are looking like they're very good for us. So we're happy with the comparison batch to batch that we get the same product, and I'll show you those. And we also do an anti-vitamin D binding, which does pick up Gcmaf to give us a comparison as to what we've actually got. These are the lectin blot I was telling you about. These are molecular markers, and we've got several dilutions of, this is one batch, and then this is a second batch, and you can see the similarity that we've got and the comparison here. This is 66,000 kilodaltons in the molecular weight markers, and this is, I think, about 42, 43, so this puts it smack bang where it should be. And because we know the lectin is specific, we know that this is Gcmaf. Yes. Yeah, it varies slightly, but I know what you mean. Obviously, we're quite happy with that, of the two different batches that we've got there, to give you an example of what we're actually doing, so that we know our data builds up. That if we get anything that's different to that, that's our alarm bells and we start changing things and giving it back to immunobiotech saying it's not good enough. We also do some activity assays. These are a little bit more tricky to set up because they require one cell line and another cell line, so you're looking at two biological entities. We do a basic proliferation assay with a murine macrophage. So we do a range of dilutions of the MAF batches that come through. We look for proliferation and we see it being repressed, and I'll show you an example of that, of our actual results. We do an activation assay. So we do a phagocytosis. So we activate our macrophages for about 3 days, and then we put them on some carcinoma cell lines. At the minute, primarily we used MCF7s, which is the breast carcinoma cell line, but we've got a couple of other cell lines in as well that we're trying to adapt to the protocol so that we can look at other cancer cell lines. So these tend to grow as monocultures, and we can clearly see the monolayers disrupted after 72 hours with the activated macrophages. And we also do a small morphology alteration kind of assay to know that, I think it was just mentioned by Marco, that Gcmaf changes the morphology in itself, and we set that up in monolayer plates, 12-well plates, and look for that as well, just with straight application of Gcmaf. Those are the 9 tests that we do, and they're pretty comprehensive. This is some results of a couple of batches of our samples here from batch to batch. We have a blank, we have a GC globulin, and then we have 2 samples, and these are duplicates of the globulin and the blank as a range. We look for a repression of proliferation. So the pink is red on the left-hand side, which is the percentage, and the dark colour is red on the actual optical density that we see. And you can see that here's the blank with nothing added, and then the GC globulin, and then the repression of the proliferation in the presence of Gcmaf, and it's consistent from batch to batch. And likewise, you can see that the actual negatives and the control samples are also similar. So we build up this bank of data on each batch, and we use that for comparative purposes for consistency. This is not an unknown phenomenon. This has been seen before with the repression of cell proliferation. In this paper, I have to say that we've started to form an alliance with the University of Florence and Marco Righerio and his research group, so it's helping us quite a lot in what we're trying to do. And this is some of the data from that group showing that, again, that phenomenon is not unknown. So we're consistent with the kind of cells. These are with MCF7 cells as opposed to the neurone macrophages, but the principle's the same. Obviously, the amount that's repressed is going to be variable cell line to cell line. So we're quite happy with that. And to give you another indication here, this is MM6, which is a human monocyte macrophage. We use murine at the minute. We do have a human macrophage lining that we're just culturing up to use and cross over so that we have human-human interactions to make it more consistent. But you can see that, again, Gabriel Marucci, he's looked at first immune Gcmaf on cell lines, and you can see the repression that's against the blank, and then this is against a probiotic application, which will be talked about, I think, tomorrow. So we're quite happy that we're consistent. Everything's matching up to what's in the literature, so our assays, we feel, are being validated in that way. To give you an example of the activation assay, this is the monolayer. Here, you can see the cells, as it's been explained, they grow above the monolayer and they sort of come up in great masses. So what I do is, with the activation assays, is we put them in 12-well plates on a microscope slide, which is heated. I use heat these as a buffering system for that. And then I take a blank photo. I put it back in the cabinet. I add my activated macrophages, try and get it back into the microscope in the same space. And then we sort of do a time lapse on it. And then in this particular example, after 145 hours with the added activated macrophages, you get complete clearance of the monolayer. It's just completely destroyed. After about 72 hours, you can see quite about 70% of the actual monolayer is disrupted and it is breaking up. And you can alter that speed by activating with higher amounts or putting in more macrophages. So we've got a good cell ratio of macrophages to breast carcinoma cells, which works, and we always get it in the same time frame. So again, our activity assays we're quite happy with. The morphology alteration assay, to give you an example here. Here again is a monolayer, and you can see two masses that are growing well above the actual monolayer itself, so they're growing up 3D into the media. And after 72 hours, you can see these are much less, and they've decreased. And if you have a look at the cells which are around, so this is just with the addition of Gcmaf only. Again, that follows what we've seen in the literature from Marco Ruggieri's group, that we can see the same effect with the Gcmaf that we get, and we run that assay on every batch, so we know what we're expecting and what we can achieve.